Well, hello there, Math 1314 class. I hope everyone's doing well. This is Mr. King again, and I'm here to make the second part of the lecture video for section 2.2, and I hope it can be helpful to you. So we'll finish it up, and I wish you the best. Okay, let's do some mathematics, class. Okay, class, so the part 1 video, I had to abruptly stop it, and I apologize for that. But I'm switching to, I've been using Screencast-O-Matic instead of Zoom. And once you get to 2 hours or beyond, in length, it makes it very difficult and time-consuming. Not difficult, but time-consuming to upload it and put it into Blackboard. So that's why I had to abruptly end it. But we just barely finished problem 25 and inputted the answer here. And then I didn't even get to say goodbye because I was only a 1 second within 2 hours. So I apologize for that. Let's continue then. And I would like to help you, same type of problem, but with number 27. And they give us 3 zeros again, like this one up here. It's just that 2 of them are irrational zeros. And you notice they're conjugates of each other. 9 plus square root of 2, 9 minus square root of 2. Those you have the same 9, 9 plus square root of 2, and then one of them is plus and the other one's minus. And so from that, and the 3 zeros, we're going to build a polynomial that will have these 3 numbers as their zeros, as their x-intercepts, as their roots. So if we go to decimals and we do something similar, I still have it here, from the problem number 25. And I'm just going to, well, now I'm going to change these, of course, and now we have the following zeros. One of them is 4, so I'll change this one from -4 to +4. And see, it moved over here, of course. And the other 2 happen to be irrational solutions, or zeros, which means if we, because the square root of 2 is irrational, it's 1 point, well, let's see. The square root of 2, what it shows that it stops here, but this is rounded. It goes on forever. And the digits go on forever. It's irrational. It cannot, excuse me. It cannot be, it doesn't, like I just said, it doesn't end, so it's irrational. You can also say you can't write it as a fraction or as a, but that's another story. Okay, so if we look at 9 plus square root of 2, 10.41, that's still irrational. It's just now it's 9 units bigger than this was. And this is an actual 0. So I'm going to put this inside a grouping symbol that will represent the point. And of course, the range value for x-intercept, or a root, or a 0, is it's exactly where the point touches the x-axis, which is why it's called a 0. And so now you see, let me change this color to make it a little brighter. Oh, let's see. And maybe it's just my eyes. It seems a little dull, but oh well. So here is the x-axis. And here's one of the zeros, 4, 0. And if we move out a little bit, zoom out, here's the other one. 10.414 is the rounded to 3 digits, 3 digits past the decimal point, and then comma 0. So there's the second, or there's another one of the zeros. And the other one is the conjugate of this, 9 minus the square root of 2. 9 minus the square root of 2, let me just do that first, I guess. That'll be 9 minus 1.414-ish. 9 point this, which is 1.4 or something. And so that's going to be 7 point something. And there it is. It's a positive number. And now and that's going to be right in this, a little bit past 7. And so we're going to get a third 0 right here somewhere. Okay. So put this in a coordinate grouping symbol, comma 0, and comma 0. And there you see. So, and there's the y-axis still. Okay, right here. So now we're going to construct a polynomial that passes or touches the x-axis in these three locations. Okay, so maybe that's better. Okay. No. Okay. Okay, class, so I'm going to go back to my notebook, and we're going to do the same process we did here as here. So here we go. Okay, so here's 27. Given the zeros are 4, 9 plus square root of 2, 9 minus the square root of 2. So I didn't write as many comments as I did on the first problem, which was 25 at the end of the last video, this one. And I had more comments there, and I'm not writing all the comments down because we're just going to repeat this process. So, okay, so if the zeros are these, then the solutions are x equal to 4. The solutions to the equation, whatever we end up getting, what are the zeros to that equation? And they are these 3 zeros, which means these are the solutions: x equal to 4, x equal to this, and x equal to this, and 1, 2nd, 3rd, no particular order. If we now move these numbers to the other side, then we can call these the factors. And so if you move 4 over to the left, we get x minus 4. That's equal to 0 still. It's just a different way of writing these 3 solutions, is by moving the number back over to the other side. And then move this positive 9 over to the left, becomes minus 9. Move positive square root of 2 to the left, becomes negative square root of 2. So we get x minus 9 minus square root of 2 equal to 0. And here we do the similar thing. Move the positive 9 over, becomes negative 9. Move the negative square root of 2 over, becomes positive square root of 2 equal to 0. And so now we have all 3. We have this factor equal to 0, this factor equal to 0, this factor equal to 0. Or we can say that expression equal to 0, this expression is equal to 0, this expression is equal to 0. So in our efforts to create a function, a polynomial function whose zeros are these 3 numbers, then we continue and we say, well, if this if this expression equals 0, and this expression equals 0, and this expression equals 0, if you multiply expressions that we know equal 0, then their product will still equal 0. Basically 0 times 0 is 0. So if you tell someone, hey, this is equal to 0, and someone else brings up something to us and says that's equal to 0, well, if you multiply those two objects, they have to equal 0. if they're both equal to 0. And so x minus 4 we know is equal to 0. Now it's kind of strange. Obviously this has an x and this has a minus 4, and so it doesn't mean that literally this is gone and it's 0. It means that it's equal to 0 because it came from this. And so this is equal. So anyway, the product of these three equals 0. And see, now we have three multiplied factors equal to 0. And all we have to do is multiply them out, and we'll come up with our polynomial equation or our polynomial expression. So we have to multiply all three, but let's do 2 at a time. You have to do 2 at a time. So I'm going to choose to do this one times this one. It works out more friendly when you have this messy irrational number here, and you see there's 3 terms here, 3 terms here. And so it works out more friendly if you multiply this one times this one first, because some terms cancel out. If we were to multiply this one times one of these two, say this one times this one, then it still will work. We'll still get the correct answer. It's not quite as friendly in terms of multiplication, multiplying it out. So let's multiply this times this. So just like we talked about before, we're going to do this. This factor here has one term, a second term, a third term. This factor has a first term, a second term, and a third term. So we're going to cover up these two and now multiply x times this one, x times the negative 9, x times the positive square root 2, and that will give us 3 terms, 3 answers so far. And now this x here is exhausted in the sense that we've already multiplied it by all 3 over here. So then this is done. Now move over to the next term, which is the negative 9, and now you're ignoring the first and the third term and just looking at the middle one. And so now it's negative 9 times x, negative 9 times the second one, negative 9 times the third one. That gives us 3 more answers, 3 more terms. And now we move over. Now the negative 9 is exhausted here. It's already been we already multiplied it by these 3. So now all we have left is this third term. And the negative square root 2 times x, the negative square root 2 times negative 9, and then the negative square root 2 times positive square root 2. And that'll give us 3 more terms. So when we're done multiplying these 3 terms times 3 terms, we're going to get 9 terms, 9 of them. So we just have to be careful. And then you'll see these terms, a lot of them cancel out. So that's why I'm suggesting to multiply these 2 first. And when we're done and we get that done and we get it cleaned up, then we're going to have to multiply it by x minus 4. Okay, so here we go. So the x covering this up, it's kind of hard. So covering all this up here, we have this x times these 3. So x times x is this x squared right here. X times negative 9 is negative 9x. X times positive square root 2 is positive square root 2x. So there's 3 done. This one we're done with this one. It's exhausted. It's done. Now we look at the negative 9 times these 3. So the negative 9, I'm sure you don't need me to cover all this up. I'm just trying to help. Negative 9 times x, negative 9x. Negative 9 times negative 9 is positive 81. Negative 9 times positive square root 2, negative times positive is negative. 9 times square root of 2 is 9 square roots of 2. So now this one has been exhausted. We've multiplied it by these 3. And now we have the last one. and it's negative square root of 2 times this. So negative square root of 2 times all these three right here. Negative square root of 2 times x, negative square root of 2 x. Negative square root of 2 times negative 9 is positive 9 square root of 2. And negative square root of 2 times positive square root of 2, negative times positive is negative. The square root of 2 times the square root of 2, you put it together, and you put the 2's together inside a single square root symbol. The square root of 2 times the square root of 2, you can put them together because this is the square root and that's the square root, so you can put them together as long as these are positive. They have to be positive to put it underneath just one square root symbol. And now 2 times 2 is 4, and there's still this negative sign in front because this was negative square root of 2 times 2 square root of 2. And so the square root of 4 is 2, square root of 4 is 2 times this negative is negative 2. So anyway, this negative square root of 2 times positive square root of 2 is negative square root of 4, which is, and the square root of 4 is 2 with the subtraction sign in front of it, so we get negative 2. So I hope that's okay. Now we have our 9 terms from multiplying this times this. 1, 2, 3, 1, 2, 3, 1, 2, 3. Now, combine any of these like terms to simplify. So, this is still waiting to be multiplied once we finish cleaning this up. There are no other of these 9 terms, no other one has an x squared on it, so this one just stays the same. This is let's see, positive square root of 2 times x, positive square root of 2x, negative square root of 2x, they combine to 0, so that's friendly, numerically speaking. Negative 9 square roots of 2 and plus 9 square roots of 2, they add up to 0, so they're gone. That's what I meant by this is a little bit friendly here. Some terms cancel out. Negative 9x minus 9x is negative 18x. So these two are gone. I mean, we've not gone, but we've combined them. And 81 minus 2 is positive 79. So now we have this times this is x squared minus 18x plus 79. And now I just moved it up here, just because of paper space. And now we're going to multiply it by this now, x minus 4. And see, once we multiply this out and combine any like terms, we'll have our polynomial that should pass through those 3 numbers they gave us right here, which are the 3 zeros, the 3 x-intercepts, the 3 roots. So now we're going to multiply x minus 4 times this here. So again, same idea. You multiply, there's 2 terms here in this factor, and this grouping symbol times, there's 3 here. So when we get done, we're going to have 6 terms. So multiply the x times this one, and then times this one, and then times this one. And then negative 4 times x squared, negative 4 times negative 18x, negative 4 times positive 79. You get 3 more terms, total of 6 terms. So what about x times x squared? So we have x times x squared, positive times positive, positive x cubed. Positive x times negative is negative. X times 18x is 18x squared. X times 79 is positive 79x. So this one's done. Now we move over to negative 4 times these 3. Negative 4 times x squared, negative 4x squared. Negative 4 times negative 18x is positive 72x. Negative times positive is negative. 4 times 79 is 316. And now we have the other three terms written down, multiplied together and written down. So we have our 6 terms. Combine anything we can. Of the 6 terms, there's only one that has a cube, x cubed, so there it is. There's our degree of our polynomial, by the way, 3. And what about x squared terms? There's one right here, negative 18x squared, and here's another one. Negative 18x squared minus 4x squared. Negative 18 minus 4 is negative 22 of those x squareds. 79x plus 72x, those are like terms, x to the first, so you can add them together. 72 of those x's plus 79 of those x's plus 72 of those x's add up to 151x. And the only thing left now is the negative 316, so we just write it down again. And so these 6 terms cleaned up to these 4 terms. And so we now have created our polynomial. The polynomial p of x, p for polynomial, you don't have to call it, you don't even have to write p of x. It's x cubed minus 22x squared plus 151x minus 316. Or, and if we graph this, let's graph it. So on Desmos, so we have it right here. So we have y equals and here comes the magic moment, and we should get a cubic function, degree 3, odd degree. So the tails should be an opposing direction. It's a positive 1x squared, positive 1, leading coefficient's positive, so the left tail will be going downward and the right tail will be going upward. Maximum number of turning points, the maximum is the degree less 1. Take away 1 from the degree, that's 2. 3 minus 1 is 2. At most, 2 turning points. At most, 2. Could be only 1 turning point or no turning points. Somehow it's going to have to turn here, though, to get back up to here and come back to here. So, okay, so here's the big moment, 316, and because those numbers were big, we need to zoom out to see it. And there you can see the graph. Here's the left tail going down, the right tail going upward, which we talked about. There is 1 turning point coming down, minimum, relative minimum point, then turns around, goes back up. So there are, the maximum number of turning points was 2, and there are 2 of them. And where does the graph touch the x-axis? Where are the x-intercepts? Yeah, right here, and right here, and right here. There are the 3, and they went right through those points that we were given, because we were given these 3 zeros, and we created a polynomial that does, in fact, have these as their zeros. And these are called zeros because that's where the function has function value, range value, second dimension value, y value 0. and the x value is the actual solution, or the x-intercept, the x value is 4. It's 7.586 rounded, which is really the 9 minus the square root of 2 in exact form, and the 9 plus square root of 2 is this one right here. So there we go. So we can say we created something. Now, I had to rush this part, the next part on the last part 1 video, and so what I want to do is go over that part again. If we take this equation and we don't know why I don't see the red one. So all I did is copy it and paste it here. So of course it's the same graph. What happened was the minus 316 was missing. I didn't copy the whole part. But now I did. I see it. And now if we take this polynomial and multiply it by any number we want, of course if we multiply it by 0, it wipes it out. If we multiply it by 0, it's just going to be 0. 0 times all this is 0, and then you just get y equals 0, which is this horizontal line, which is the same as the x-axis. So that's why you'll see in the notebook in my paper, you'll say, or you can multiply this polynomial that we created by any constant you want except for 0. Because as soon as you multiply it by 0, then you're not going to have a polynomial that passes. I mean, yeah, this does pass through these 3 points, but it's not a very interesting one because it's just a horizontal line. So anything other than 0, so let's multiply it. Turn this one back on. Turn this one off. There's the one that we created. Now if we multiply it by any number besides 0, so let's say whatever, how about times 2? When you multiply by times 2, all these points are going to vertically stretch away from the x-axis. So like this will stretch double, twice as much. So that's 15.378. When you multiply it by 2, it's going to be all the way up to 30 something. And all of these points will stretch vertically. The ones above will stretch upward, and the ones below will stretch further downward. However, they will still pass through the same 3 numbers here. And that's what is unique. That's what's interesting. Times 2. And you can see that they still passes here, comes up, turns around, and you can see it stretched further out. Say the original one was purple. And they still have the same, the new one, the times 2, comes up, passes through the same x-intercept value as the first one did, turns around, just turns around, it's stretched down further, that's that vertical stretch, and now it comes back up and it touches the same x value as the original one did. If we multiply all this by another number, it'll sorry. Now I'm going to multiply it, let's say, by a negative number. Say a negative 4. Now it's starting to get a little messy here, kind of hard to see. So let me turn off this one. The purple one was the original one, and the green one, let me change the window here. So we can see it better. Let's see how that works. Well, that's kind of interesting. So there's the original one, the purple. Passes through these three x-intercept values. Now let's put on the one that we multiplied by -4. Yeah, because now it's negative. If you multiply this through, it'll be -4x cubed. Negative, and we know that means the left tail goes up and the right tail goes down. But you see, the green one here is still passing through the same three x values as the same three x-intercepts as the original one. And we can keep multiplying this by any number. And there's the other one. And we can just keep doing this forever. And that's why it says on WebAssign there are a lot of possible answers. Well, that's for sure. There's a lot. There are many. There's an infinitely many. So how the heck is WebAssign going to grade all? I don't know. But we'll just put the original one in. So let's see. We have x cubed and we could put a parenthesis around this and then multiply everything by 2 or -4 or 3 and see, and it should. They have it programmed so that it'll accept it, any of them. At least that's what it seems like. And there's our green check mark. Yeah, so we're good. So I hope that makes sense, class. Okay, next I would like to do 28 with you, which is the last problem on this homework. And then we're going to go up and look at the last piece that we haven't covered yet. Oh, we've covered most of the content, we just haven't practiced it. So, okay, 28. They give us the 0, and it's only this one, it says. It only has this one. Well, that's what it said up here, too. It only has this one solution. But yet, the degree of the polynomial needs to be degree 2. Okay, so let's take a look at that. So 28, given x equals -2 is the 0, and it's the only one. Where the degree is, we're being told when we create the equation, the degree has to be degree 2. So we know that x equals -2 is a solution, or we can say a 0, or a root. And since x equals -2 is the only solution, and we know the degree has to be 2, n equals 2, then x equals -2, the only solution we have, and can have, according to the directions, must count twice. It has to count twice. You're like, what does that mean, count twice? How can it count twice? Or we say multiplicity is 2, which means it counts twice. Which means we have to count this twice, include it 2 times. Multiple times. How many multiple times? 2 of them. Because the degree has to be 2. And since we only have one solution, then we have to count it twice. If they would have said n equals 3, then we would have had to use this 3 times. And then we would have said multiplicity 3. So, x equals negative 2 is a solution. If we move the negative 2 over, it becomes, the negative 2 becomes positive, and we get x plus 2 equals 0. But we have to count it twice. So we literally rewrite this twice. X plus 2 times x plus 2, twice. Multiple of 2 times. So x plus 2 times x plus 2 twice, because if now when we multiply this together, we will get the x times x will give us the x squared, which makes it degree 2. Another way to write x plus 2 times x plus 2 is to say x plus 2 squared. Squared. And so when we see the same factor with a squared, which we've seen in the past, we just maybe haven't thought about it this way or have learned about it yet, then we're like, oh, that means this counts twice. That means it has this 0, x equals negative 2, has multiplicity 2. It counts twice. Or we can say x plus 2 has this factor has multiplicity 2. It has to count twice. And so that's what we see, or we are now going to be thinking when we see this. You have x to the first plus 2, that's linear, x to the first. That's as far as we're going to factor it down, x to the first plus 2, or plus 4, or minus 1, or whatever. Or even just x. And then you see an exponent up here, and you're like, oh, that's the multiplicity. That means it counts twice. Or it counts 3 times. Or it counts 5 times. Whatever this is. Well, it counts only twice here. So now we're going to create our polynomial. We're going to multiply this out twice. And so now we just multiply it. So this x times these 2, and the positive 2 times these 2. And so x times x is x squared. X times positive 2 is, oh, I guess I didn't show the work here, sorry. So we would have, x times x is x squared. X times positive 2 is positive 2x. And that takes care of this one. Now we multiply it by the positive 2. Positive 2 times x and positive 2 times positive 2. Positive 2 times x is positive 2x. Positive 2 times positive 2 is positive 4. And here are our 4 terms. Combine any like terms. Well, there are no other, there's only 4 of them, and this one's the only one that has an x squared. So we write it down. 2x to the first plus 2x to the first is plus 4x. 2x plus 2x, 4x, and then the 4 still by itself. And so here is our polynomial we have created. If you write equal to 0, that just means you're asking when does that equal 0. So the polynomial, though, is just x squared plus 4x plus 4. Or we could say p of x equals x squared plus 4x plus 4. If we graph this now on Desmos, it will have to cross the x-intercept. It will have to cross the x-axis at x equals negative 2. And then we're going to talk about what does it mean graphically when it's counted twice, when it has multiplicity 2. So let's go to Desmos. I'm going to clear all this out here. And we'll graph x plus 2 squared And you can see the graph comes down and touches right here at x equals -2. So it has that x-intercept right there, or the zeros right there. It turns around right there and goes back up. If we multiply that out, we had y equals x squared plus 4x plus 4, and it's the same graph. This is the same as this. That's why you don't see anything different. This is degree 2, even degree. That means the left end and the right end have to be in the same direction, either both going upward forever to infinity or downward forever to negative infinity. Because this is positive in front, the leading coefficient is a positive number. There's a multiplied positive 1 there. You can't see it, but it's there. It's always there if we need it. Or even if we don't need it, it's there. Positive means the left and the right end go upward. As you can see, they do. Now, if we multiply this by any constant other than 0, multiplied by any constant, say 3, the green one is the new one, and you can see it still touches the x-axis at the same point as it did as the other one did. If we multiply that by a negative number, well, I'll just change it to a negative. Well, now it opens downward. And you can, if you did multiply this through, you get negative 3x squared minus 12x minus 12. And yeah, there's a negative number in front of the highest degree term, and that means both tails have to go downward, which they do. So now I want to go back, we'll go back and put it in WebAssign in a moment, but I want to talk about this multiplicity 2. So I'm going to erase the green one here. This multiplicity 2 tells us something besides the x plus 2 was counted twice, or x equals -2 is a solution. It is a 0 that has multiplicity 2. Yes. When we have multiplicity, an even multiplicity, 2 is an even number. Let me just first finish the WebAssign part so that we can just get that out of our mind for our own. And so right here, we'll just type it in. Y equals x squared plus 4x plus 4. And we also, oops, what did I do? I don't know. Maybe it doesn't want the y equals part. Yeah. Here they wrote it over here, f of x equals. Here they didn't write anything, I guess, and they just wanted that part only. So, okay. So we're done. You could also have put a parenthesis around this, multiplied it by any number you like we multiplied it by, I don't know what it was, -3 or something. Check it, and it should still be correct, because this also will pass through. Yeah. So they do have it programmed for that all those different answers will work, because they should. Okay, very good. Now, this one will be for you. It's very much like this one down here, except you don't have a third one. So that makes it a little less work. And so that's why I picked this one instead of this one's for you. and this one should be really short. It's just like this one here. Well, it's just like all the other ones. It's just that there's only 2 of them. Okay. Now, before we move on to this last piece, I want to go back to Desmos and make a comment. I'm going to write this here again. Oops. And change this to an odd multiplicity. So what if we make this a 3? So notice, when we have this is the same factor multiplied twice, or we can put exponent 2. This is x plus 2 multiplied 3 times. So this would be x plus 2, a factor x plus 2 with multiplicity 3. This is a factor of x plus 2 with multiplicity 2. Another way to say that is this has a 0. X equals negative 2 is where it crosses the x-axis, and so is this one. But this has a 0, x equals negative 2 with multiplicity 2, and this one has x equals negative 2 as a 0, or as an x-intercept, or as a root with multiplicity 3. And so, well, notice the graph's different, that's for sure. And what happens, class, which is one of the last things that we need to cover, which is fairly nice, it's not difficult, is if you have odd multiplicity, odd, then when the graph touches the x-axis at that 0, which is x equals negative 2, notice it comes up, the purple one, this is the odd multiplicity, comes up and touches the x-axis, but it doesn't turn around and go back down. It just keeps going upward. It keeps going in the same direction. So here, the graph will touch the x-axis, but pass and just keep going in the same direction. And when it's even multiplicity, the graph will touch the x-axis as well, obviously, because it's a 0, it's an x-intercept at x equals negative 2. But then it turns around. It turns around. It's a turning point. And so, when you have even multiplicity, it's going to touch the x-axis, but then it's going to turn around and go back. It's a turning point. When it's an odd multiplicity, it's going to touch the x-axis, but it's not going to be a turning point. It's not going to be a turning point. Notice if we put something extra now, just make something up. X plus 1 and let's say here we make it squared. How about I make this a minus 1? Yeah, we got to be careful. We might miss part of the graph, huh? This has multiplicity 3. X equals negative 2 is the root for this one. X plus 2 is the factor. X plus 2 is a factor with multiplicity 3. There's three of these x plus 2 factors multiplied together. Or you can say it's going to give us the root, the 0, the x-intercept, x equals negative 2, and it's going to count 3 times. It's going to have multiplicity 3, which is odd. Odd multiplicity means the graph is going to touch at negative 2, but it won't turn around. It touches it and keeps going in the same direction. It doesn't turn around. here is the other x-intercept, the 0, the root. What kind of multiplicity does this factor have, x minus 1? It has multiplicity 2, which is even multiplicity, even. Or you can say, because there's x minus 1 is the factor with multiplicity 2, well, that means it's the 0, the x-intercept, the root for this factor will be the opposite of this number, positive 1. X equals positive 1 will be an x-intercept. X equals 1 will be a root. X equals 1 will be a 0 with even multiplicity, with multiplicity 2. And its even multiplicity means it's going to come and touch the x-axis at x equals, in this case, 1, but it's going to turn around. And notice it turns around. So, odd multiplicity, even multiplicity. Okay. Okay, so let's go on. And okay, class, so now we're going to look at the last part of this assignment, of this section, and that is going the other direction. So instead of creating the function when they give us the zeros, like we have been doing, now we're going to go the other way around, and they're going to give us the equation, give us the polynomial, and we go and find the zeros instead. So instead of us taking the zeros, putting them back as solutions, writing them as factors, multiplying them together like we did, we, for example, again, we took the 3 given zeros, 2 of which were irrational, this one and this one. Instead of taking those zeros, writing them in as these equations, and then multiplying these equations together to get the 3 factors, multiplying them all out, reducing, cleaning it up, and getting the actual polynomial equation that had those roots. Now we're going the other way, and well, it would be like starting with this equation and finding what the 3 zeros are, and getting this one, x equals 4, getting this one 9 plus square root of 2, getting this one 9 minus square root of 2. And so that's what we're going to do now. And we're going to look at number 20. And notice on number 20, it's partially factored. Number 20, g of x equals 3 times x times the quantity x squared minus 4x minus 1. This x has already been factored out of these 3 terms. They just gave it to it that way. It's kind of like when we were let's see if I can find what I'm looking for. It's like this first problem number we did together, number 25, when they gave us these zeros, 0, -2, -4. We put it back together, and then we got to write, we multiplied them together, equal to 0, multiplied these 2 out, got x squared plus 6x plus 8, and now we rewrote it here. Now we have this other x minus 0, which came from here, which came from here, which came from here. X minus 0 was x, and then we were right here, x times x squared plus 6x plus 8. And that's where they give us, and that's how they give us the equation right now. There's an extra times 3 in front on our problem we're about to do, but that's okay. That's not a problem. A multiplied number in front. And so this is where we are going to start. It would be like if we're right here. And so let's take a look. So here are, again, it is, this part is factored out already, the times x. There's a times 3 there. If we wanted to, we could put the times 3 right inside and say 3x squared minus 12x, 3 times negative 1, negative 3. But it's taken out, and so that's good. It makes these numbers in here smaller, so that's good. Okay, so now remember, we're not being asked to create the polynomial, but we're being asked to find the zeros. So we need to break, we have this factor 3x, and we have this factor x squared minus 4x minus 1. So we set each of these equal to 0. So 3x equals 0. And then to solve for a multiplication of 3, we know we divide both sides by 3. 3 divided by 3 is 1 times the x that's already there. 1x and 0 divided by 3 is 0. So we have one solution already. So we have one of our zeros. X equals 0. That's a root or a 0 or an x-intercept. And now this x squared minus 4x minus 1, notice the degree here is 2. That's going to give us 2 more zeros, 2 more roots. And now we need to find them. If we can factor this down, well, then we try. Or if we're not able to factor it, then we have to use the quadratic formula. And so that's what we're going to have to do here. X squared minus 4x minus 1 it's not possible to factor it as this times this, like that. If you kept trying x times x squared, that's a negative, so 1 would have to be positive, 1 would have to be negative. The only way you can get 1 is 1 times 1. If you multiply this times this back out, you will not get this up here. And it's impossible for us to factor it like that. So when we have a quadratic that has 2 roots or 2 zeros or 2 x-intercepts, and we're not able to find them by factoring them down into 2 linear factors, well, then we use the quadratic formula to find those 2 zeros, to find those 2 x-intercepts. So recall, so I just rewrote the x squared minus 4x minus 1 from right here. The a is the number, the multiplied constant in front of the x squared term. So a equals 1. There's always this multiplied 1 here. B is the multiplied constant in front of the x term, x to the first term. B equals negative 4. And C is the number by itself without an x on it. So A, B, C. A is 1, B is negative 4, and C is negative 1. And here's the quadratic formula, of course, to get our x values. And by the way, we're going to get 2 of them because this is degree 2. So by the fundamental theorem, we're going to get 2, unless it's a repeated one with multiplicity 2, but this is not going to factor into the same thing twice. We're not going to get the same answer twice here. So now we use this quadratic formula, negative 1 times the b value plus or minus the square root of b squared minus 4 times the a value times the c value, completely divided by 2 times a. Notice this plus or minus is what is going to give us our 2 answers. Just like the problem I was just showing you, we had the 9 plus the square root of 2, the 9 minus the square root of 2. Yeah, that's what will happen in this kind of problem here. We're going to end up getting two irrational numbers. 2 minus square root of 5, 2 plus square root of 5, and just like that problem when we went backwards and they gave us 9 plus square root of 2 and then 9 minus the square root of 2. Okay, so let's fill in the appropriate numbers for these letters. So using the quadratic formula to get our x-intercepts, we have x equals -1, and then right here we put the b value, which is the -4, plus or minus square root. I suggest you put these little grouping symbols so that we're less likely to make an error with these negative signs. -4 goes inside to b squared, and if we don't put the -4 inside this parenthesis, it's more likely we can make an error when we multiply this out. So that's my recommendation. Subtract 4 times the a value, which is the 1, which came from right here, times the c value, which is this one, which is the -1, divided by 2 times a, where a is equal to 1. Now, this will give us our two solutions, our two x-intercepts, our two roots, our two zeros. In the denominator, now we're going to clean this up, simplify it. 2 times 1, of course, is 2 in the denominator. -1 times -4 is this 4 right here, plus or minus from right here, plus or minus. That's what's going to give us the two solutions. The square root, -4 quantity squared is -4 times -4, which is positive 16. -4, well, how about it doesn't, -4 times 1 is -4 times -1. -4 times -1 is positive 4. 16 plus 4 is 20. So now we have 20 inside here. All this cleans up to just 20 inside the square root. So we have 4 plus or minus the square root of 20 divided by 2. To break down the square root of 20, we can break down 20 as multiplication of two numbers, and one of these two numbers is a perfect square number. 4 is the perfect square number because we can say 2 times 2 is 4. And so we know that if we break down this 20 and split it up into 4 times 5, one of these numbers we can take the square root of, and that's the 4. Yeah, not the 5, but the 4 we can. So now we split these apart. Square root of 4 times square root of 5. The square root of 4 is the 2. And then the square root of 5 we cannot simplify. We can't take the square root of that. You can't break 5 down anymore, except for 5 times 1, and that won't help. It won't help us taking the square root of anything. So we're going to end up with 2 times square root of 5. So this right here becomes, right here, a 2, and then times the square root of 5. And so now we're come over here now, and now we're going to write 4 plus or minus, instead of writing the square root of 20, we're going to write 2 square roots of 5. 4 plus or minus 2 square root of 5 divided by 2. And then I picked one of those is a subtraction and one of them is a plus, addition. I just picked the subtraction one and I wrote it right here. So 4 minus 2 square root of 5 divided by 2 right here. And over here I wrote the plus. But before we do that, let me continue on this other path. So the 4 minus 2 square root of 5 divided by 2, there's two terms in the numerator, the 4, the 2 square root of 5, because it's in between is a subtraction sign. So this subtraction sign again separates this into two terms. And both of these two terms are to be divided by 2. So we can separate it as this term divided by 2 and this second term divided by 2. So we get x equals 4 divided by 2 minus 2 square root of 5 divided by 2. 2 square root of 5 divided by 2. 4 divided by 2 is 2. This 2 divided by this 2 is 1. 1 times the square root of 5 is still square root of 5. So we'll have here, this reduces down to 2 minus the square root of 5. So here's one of our zeros, x equals 2 minus the square root of 5. Once you get this irrational answer, you're gonna with the quadratic formula. Well, the other one's going to be 2 with the square root of 5, but a plus sign in between. And so that's what we're going to see here. So the 4, so just like this one, 4 over 2, 2 square root of 5 over 2, but instead of a subtraction sign, now we have the plus sign. And now we divide these again. 4 divided by 2 is 2. This 2 divided by 2 is 1. So we get 1 square root of 5 plus 1 times square root of 5. But you don't have to write the 1 right there. It's there, but we don't have to write it. And so here now we have our two zeros that came from this quadratic factor here, x squared minus 4x minus 1. We weren't able to factor it ourselves, so we used the quadratic formula, and now we have them. And so now we take these two answers with this answer here, and we have our 3 zeros. And our 3 zeros are x equals 2 minus the square root of 5, x equals 2 plus the square root of 5, and we also have the x equals 0 from right here. So here are our 3 zeros, all of which, well, we'll go to WebAssign, find all real zeros of the polynomial function. Use commas to separate your zeros in your answer box. If there aren't any solutions, enter no solution. So one of them is x equals 2 minus the square root of 5, comma. Another one was 2 plus the square root of 5, comma, and another one was x equals 0. And then it asks us the following: determine the multiplicity of each zero. Determine the multiplicity of each zero. So remember, class, back with this problem 27 that we did a while back, we had these given zeros to us. X equals 4, x equals 9 plus the square root of 2, x equals 9 minus the square root of 2. And then we had to create the equation, create the polynomial that had these 3 zeros. And so once we wrote these down, then we moved this over and we got x minus 4 equals 0. Move this over, became x minus 9 minus the square root of 2 equals 0. And then we had, move this over, and we had x minus, move the 9 over negative, move this negative over positive, x minus 9 plus the square root of 2 equals 0. And then if all of these are equal to 0, then we recall we multiplied them together, and then they had to equal 0. So then we wrote x minus 4 times this equals 0. Then we multiply these out to come up with our polynomial equation. But what I want to do is stop right here. And notice we have our 3 factors multiplied together equal to 0. And these 3 multiplied factors came from right here, which came from right here, which came from what they told us in the directions. And we know that when you have this, there's an invisible exponent right here. If you don't have anything there, we know that's a 1, and that's a 1, and that's a 1. So this factor is of multiplicity 1. This factor has multiplicity 1. This factor has multiplicity 1. If you add up all the multiplicities, they add up to 3. And notice when we got our equation, it was x cubed was the highest exponent, so it's a degree 3 polynomial. And whatever your degree is of your polynomial, in this case it's degree 3, then in your factored form, the multiplicities always have to add up to the degree of the polynomial. So this degree was 3, and these multiplicities do add up to 3. All of these were odd multiplicities because the multiplicity 1. And so for our problem 20, we were asked to find the zeros of this equation right here, which is a polynomial. We did. We have right here x equals 0, x equals 2 plus the square root of 5, and x equals 2 minus the square root of 5. If we were to move these terms over, these numbers over like I just showed you above, we would move the 2 over, it would become a minus 2. The negative square root of 5 would become a plus square root of 5. This positive 2 would become a negative 2, and this positive square root of 5 would become a negative square root of 5. And here would be these two factors with degree 1, degree 1. And then we also had this x equals 0, which came from here, which really came from here. So we could either write just x right here, but it was really a 3x. So put the 3x there. That's also multiplicity 1. And so these three factors, which came from these three zeros, which we found, all have multiplicity 1. If you add these multiplicities up, 1 plus 1 plus 1, that's multiplicity 3. And if we were to multiply this 3x through here, we would get an equation, excuse me, 3x times x squared is 3x cubed. 3x times negative 4x is negative 12x squared. 3x times negative 1 is negative 3x. That's what this equation was, or can be written as. So notice the degree of this equation that has these three zeros is a degree 3 polynomial, degree 3. The leading coefficient is positive 3, which means the left end behavior is going to go downward, and the right end, or the right tail, is going to go upward. Maximum of 3 minus 1 is 2 turning points, maximum of 2 turning points. Remember, we talked about the multiplicity. If you have odd multiplicity, then if the zeros have, or the x-intercepts have an odd multiplicity, that means the graph is going to touch there at the x-axis, but not turn around. So all three of these zeros have multiplicity 1, which are odd, and that means none of them will be turnaround locations. Those x-intercepts there will not be, there won't be any turning around going on right there. If we go to our WebAssign now, number 20. This is what we had. Here are our zeros. Determine the maximum number of turning points, which we just talked about. It was the 3 minus 1, the degree 3 minus 1, or add up all the multiplicities, and that gives you the degree. The one, each one of them had multiplicity 1, so it added up to 3. 3 minus 1 is 2, so there's a maximum of 2 turning points. Maximum. That's this part. Letter C. The smallest zero, determine whether the multiplicity of each zero is even or odd. Well, we just talked about that all three of them had multiplicity 1. So all of them had multiplicity 1. So that's odd multiplicity. Odd multiplicity. Odd multiplicity. The smallest x value was the 2 minus the square root of 5. That's the one you'd write first. If you put 2 minus square root of 5 in a calculator, two minus, well, let's do this one. So we have 2 minus the square root of 5. We can put that point down. 2 minus square root of 5, comma, not inside, outside, 0. There's one of the x-intercepts, and that's right here, negative 0.236. Another one is 2 plus the square root of 5. .23 something. You can graph that point. And that's right here. And the other one was 0, 0. Was x equals 0, which means the point 0, 0. 0, comma 0. Notice how close these are together. I'm going to zoom in a little bit so there's some separation so we can see it better. So the polynomial has to hit the x-axis, touch the x-axis right here, and right here. They didn't give us these three. We figured them out as we just did the problem. And now we're just kind of checking to see what does the graph look like now. If we go and type the equation in, remember that was this one right here. That's what they gave us. Or you could type this one in. Same thing. So if we do that, so y equals 1, what they gave us was 3x times the quantity x squared minus 4x minus 1. That was right here. Looks kind of small now. And we also multiplied this out, and we got y equals 3x cubed and we had minus 12x squared. And then we had minus 3x. And notice red graph, blue graph, they're the same. This is the one they gave us. Turn this off, and there it is. And notice the left tail is going down, the right tail is going up. This turning point is way down here somewhere. And so the left tail is going down. It comes up here, as you saw, turns. That was one turning point. Comes down. This is a second turning point. And then it goes up forever. And that makes sense based on this. It's degree 3. Tails are opposing each other. This is positive leading coefficient, so that means the left tail goes down and the right tail goes up, which it is. The degree is 3. 3 minus 1 is 2. Maximum of 2 turning points. Here's one of them. And the other one, right there. There are 3 zeros, 3 x-intercepts, 3 roots. Here's one of them. Here's the second one. Here's the third one, which we found, which is this number, and 0. And notice what's happening right here on all these x-intercepts. Because remember, these 3 zeros had odd multiplicity. They all had multiplicity 1, which means when the graph touches the x-axis at these x-intercepts, at these zeros, it doesn't turn around right there at that x-intercept. See right here, the graph is not touching and turning around. It just keeps going. Right here it almost can get confusing because you go, there's a turning point, but that's not, the turning point's not right here, it's up here. That's not the x-intercept. Just that they were so close together, it can potentially confuse us. Right here the graph comes up, touches the x-axis, that's the x-intercept, that's the 0, which is really this number right here, negative 0.236, rounds up to a 1. And then it comes up and it doesn't turn around right here, it just keeps going. Now this is a turning point, but it has nothing to do with this one. It doesn't have anything to do with this x-intercept. Then it comes down, touches again at x equals 0, and that also had odd multiplicity of 1, which means right here, when the graph touches the x-axis, it doesn't turn around here either. It just keeps going, and keeps going means keeps going downward, because this was coming down. And then the other one I already showed you. Same with this other one. Okay, so I hope that helps everyone. And so, when they say smallest x value, the smallest one was this one, 2 minus the square root of 5. And the largest one is this one, 2 plus the square root of 5. And this one's in between. So if these were different, you know, maybe one of them was even or something, you'd have to know this one is the smallest one, this one is the largest one, and this one is the middle one. Okay. Now just match. So all of them have opposing end behavior. Left end going down, right end going up. So that doesn't help us. We knew that one of them was 4 point something, because this one right here turns out to be 4.3 or something like that from our calculator. 4.236. So one of them is a little more than 4. One of them's right here at x equals 0, and one of them was negative 2.36. That's the 2 minus the square root of 5 again. So, well, this one is out because it doesn't cross over here at 4 point something. Same thing here. This is out. This one's out because it's before 4. It's not after 4. Well, this is the only one that's left. So, and this looks right here looks like 0, and the other one is right here at negative. I mean, it's kind of hard because it's not zoomed in very well. But that's believable. 4.2 something is believable. x equals 0 is believable, and right next to it is somewhere is believable, and also we know that these are all eliminated, so then this is the only one that's possible. So we turn that one as our answer, and of course there's the green check mark. Okay, so hope that makes sense, everyone. So that was 20. I would like to help you. So you're going to do 21. That one's for you. This one you can factor, right, if you like, into two factors, or you could use the quadratic formula here as well. I would like to help you with 22. So let's do that one. And also 23. So 22, t to the fifth minus 4t cubed plus 4t. There are three terms here. 1, 2, 3. This is t to the fifth. That's the highest exponent on the t's. That's t cubed, and that's t to the 1, t to the first power. So this is degree 5, degree 5 polynomial. There's at most, take the degree and decrease it by 1 unit. 5 minus 1 is 4. There's at most 4 turning points to this polynomial. At most 4. So it could be 4 turning points, or 3 turning points, or 2 turning points, or 1 turning point, or no turning points. This is odd degree. Odd degree. That means the tails, the end behavior, are opposing each other. And since it's a positive 1 in front of this highest degree term, then the leading coefficient is positive 1. Positive means, remember, the left tail has to be going downward and the right tail has to be going upward. So like this one, the left tail is going up, so this one's out. The left tail is going up, this one's out. So it's either this one or this one. The left tail is going down. The right tail is going up. The right tail is going up. So it's either this one or this one. How many turning points does this one have? There's a turning point. There's a second turning point. A third one. A fourth one. So 4 is okay, because it's going to have maximum of 4 turning points. This one has 1 turning point and a second turning point, and that's possible as well. So at the moment, either one of these is still possible. Well, before we go any, so right here we can put the maximum is 4 turning points. And then we need to figure out the zeros. Once we get the zeros, we'll, like, if it was like t equals 4 or something, then we'll move the 4 over and get t minus 4 and get the multiplicities so that we can answer this part and also know what's going on at those x-intercept locations. Is the graph touching and just keeps going through, or does it touch and turn around? Well, let's go ahead and figure out these zeros then. So we're going to look at this on our paper, factor whatever we can, and go from there. So here we go. Here is the equation, the polynomial expression right here, with an equal sign and naming it. Then we have this equation named g of t. Instead of x's, they have t's, which is okay. So this, we can notice this has a t to the fifth. That means t times t times t times t times t 5 times. This is t cubed, t times t times t, and this is a t to the first, a single t. We can only, so we can take one multiplied t out of all 3 of these terms. We can take a single 1 multiplied t, or factor out a multiplied t, but only one of them. You can't take 2 out because there aren't 2 of them right here. There's only 1. You might say, no, there's 4 of them. So that's a good question if you're thinking that. 4t means t plus t plus t plus t. Addition. 4t does not, it does mean 4 t's, but it's addition. And 4 t's multiplied together mean t to the 4th power. So that can be a confusing, a point of confusion there. So I hope that makes sense. So when you have 4t is 4 t's added together. 1t plus 1t is 2t plus another 1t is 3t plus one more is 4t, yes. T times t times t times t is t to the 4th. When we say factor out anything that it's a common factor, that means anything that we take it out as multiplication, as a multiplied object in front. And there's only one multiplied t here. There are 3 multiplied t's here and 5 multiplied t's here. So you can't take, you could take 5 out of this one, but you can't take 5 out of this one, and you can't take 5 out of this one. The most you can take out is just 1, because this one only has 1. So t times t to the 1st. How many multiplied t's are left out of this term? Well, there were 5, so now there's only 4. Excuse me. Minus 4 still. This 4. This 4. There were 3 multiplied t's. If you take factor 1 out, there's 2 left, so t squared. Plus, you take the multiplied t out, and now there's just the 4. And of course, if we multiply this back through, we should get back to this. T times t to the 4th is t to the 5th, and so on. Now, let's see if we can factor this. So, this is already to the 1st power, so we can't factor this down anymore. So we have t right here still. Now, and we have this still. And we want to know, when does that equal 0? When does this ever equal 0? So this one is nice for us right here. T equals 0. So that's going to be right here. T equals 0. And that's going to be one of our zeros. And then because this is t to the 1st, that's multiplicity 1. Here we have t to the 4th minus 4t squared plus 4. That's going to count for 4 of our zeros, for 4 of them, because there has to be 5 altogether. Or there has to be 5, a total of 5 multiplicity. Well, let's see, can we factor this? Well, it does factor. T squared minus 2 times t squared minus 2 gets back to this, because t squared times t squared is t to the 4th. T squared, remember, cover these up. T squared times negative 2, let's check it. Is this correct? So we cover this up. T squared times t squared is t to the 4th power. Now there's this t out here still. We're not talking about that part. It's just sitting there. T squared, trying to get my out of the way here. T squared times negative 2 is negative t squared. Negative 2t squared, sorry. And now this one's done. Now multiply negative 2 times this one and negative 2 times this one. So we get negative 2t squared. Negative 2 times negative 2 is positive 4. Negative 2t squared minus 2t squared is minus 4t squared. And so you can see this factor times this factor is the correct factorization of this, because if we now multiply it back out, we do get back to this right here. Okay, so we couldn't proceed if we're not able to factor this down to these two, then we're stuck, and there's really nothing we can do. So hopefully we have to be somewhat practiced now with our factoring skills. Otherwise, we're in a bad situation here on these kind of problems, because we have to be able to factor. Okay. Now what? We have this is one factor. It's t to the first. That means you can't go any further. Once you get down to the first power, that's it. Linear factor. This one is t squared minus 2. T squared minus 2. It's a repeated factor. This is t squared, which means this counts for 2 zeros. This counts for 2 more. That's 4 total. And this one counts for 1 more. That's 5. Except this and this are repeated. So we can write this one times this one as t minus 2 quantity squared, which means whatever zeros we get from this factor right here, t squared minus 2, whatever we get out of this, each of them are going to be multiplicity 2. This is going to give us 2. This inside part is going to give us 2 zeros. But each one of them are going to be counted twice because of this multiplicity 2 out here. So you can look over here and write one of these down and set it equal to 0, or you can look right here and just, since it's the same thing twice, you can just write it down once. And now we solve it. And this has to give us 2 solutions because of this t squared right here. And what the 2 solutions we get are both going to have multiplicity 2, not because of this squared, but because of this out here, because of this repeated factor. So now we take t squared minus 2, set it equal to 0. Now solve it for t. To get rid of a subtraction of 2, we add 2 to both sides. And when you add 2, you get t squared equals 2 right here. How do we get rid of a squaring function? A squaring, the mathematical, this is a mathematical operation, just like subtraction or addition. And how do we get rid of a powering of 2? Well, the inverse mathematical operation to powering by 2 is to square root, is to root it by 2. Root it by 2. So the square root of t squared and the square root of 2. Take the square root of both sides. The square root of t squared is t. The square root of 2 we cannot simplify, but it gives us the 2 answers, and one of them is positive and one of them is negative. The square root of 2 we can't reduce unless we put it in a calculator and round it, but they don't want us to round it. Leave it in exact form. So we now have this factor, which came from right here and from right here, which there were 2 of them. They give, one of them by themselves gives us t equals negative square root of 2 with multiplicity 2 because of this right here, this 2 power, because it, or over here because it repeated. And the other solution we got was t equals positive square root of 2. So this 0 right here has multiplicity 2. This 0 right here has multiplicity 2. That's a total of 4 multiplicities, plus this one right here, which is t equals 0. This is one more multiplicity, so that's a total of 5, which is what we had to begin with, 5. Another way to think of that is if we move this number over like we were doing throughout this lesson, and we would move positive square root of 2 to the other side, we would get these factors. So we already have the t minus 0. That's one factor. And that's multiplicity 1. That's this one. If you move the 0 over, t minus 0. This one, if you move this negative square root of 2 over to the other side, it becomes t plus the square root of 2. But it's repeated because it has multiplicity 2. It has to be 2 of them. So there's another one. T plus the square root of 2. And then the same thing with this one. Move the square root of 2 over to this side and it becomes negative square root of 2. Or minus. And that also has multiplicity 2. Multiplicity 1, multiplicity 1, multiplicity 1, multiplicity 1, multiplicity 1. 1 plus 1 plus 1 plus 1 plus 1 is adds up to 5, which is what it has to do. Because this is degree 5. It's just that we're not going to say there's 5 zeros because some of these are repeated. They're written multiple times, twice. So then we can change all that into all of this can be written as, sorry I don't have much space here, this is zoomed in and there's a very little space, t minus 0, which you don't really have to write, times t plus the square root of 2 with multiplicity 2. It counts twice. And the same with the other one. So here is this polynomial they gave us can be written down in factored form like this. This is multiplicity 1. So t equals 0, that's this one from right here, is t equals 0 is x-intercept, and it has multiplicity 1. This factor here came from t equal to negative square root of 2. So t equals negative square root of 2 is a 0, is an x-intercept of multiplicity 2. And the same with this factor, which came from this one, which was t equals positive square root of 2. And that also has multiplicity 2. So 2 of these zeros have multiplicity 2, or we say even multiplicity, and one of them only has odd multiplicity 1. This one multiplicity, this has multiplicity 2. This has a multiplicity value of 2. 2 plus 2 is 4, plus 1 is 5, and we still get back to the 5. And this means if it's an even multiplicity, that means these x-intercepts, the graph's going to touch the x-axis there and turn around. And this one is odd multiplicity, which means it's going to touch the x-axis but keep going, not turn around. Not turn around. So at t equals 0, it's not going to turn around right there. It's just going to keep going. At t equals negative square root of 2, it's going to touch the x-axis at negative square root of 2 and turn around. And the same with positive square root of 2. So here we have t equals negative square root of 2, comma. And when you have these square roots, you got to move the right arrow button, because if you put the comma right now, it's going to be inside and it'll say error. So you don't want that. So move it one, the cursor, then put your comma, and then positive square root of 2. Move the cursor to the right, comma, 0. Let's check, make sure we have those correct. We do. This was correct. And the smallest t value, the smallest 0, the smallest x-intercept, which was this one, had even multiplicity, multiplicity 2. The largest one is the positive square root of 2. That's larger than 0. That also was even multiplicity, multiplicity 2. And the middle one was the 0, and that was multiplicity 1, which is odd. Now let's check which graph. Remember, we already crossed out these two. And that was either this one or this one. So now that we know the x-intercepts and we know that whether it touches and turns around at those x-intercept or just does not turn around. So let's see. There are only 3 different x-intercepts, remember. There is the negative square root of 2, but it counts twice, multiplicity 2. T equals 0, multiplicity 1. T equals positive square root of 2, multiplicity 2. The square root of 2 is 1.4 something. The square root of 2 is 1.4 something. So one of them is negative 1.4, positive 1.4, and 0. So there's only 3 of them. So let's see, this one has 1, 2, 3. This one has 1, 2, 3. Okay. This one, this is 1, 2, 3, 4, 5. This to me looks like it's a little bit inside or right at 1. This one looks like it's a little past 1. This is at 0. Well, so is this one. This is negative 1.4. That looks believable. This one is negative right around 1, or maybe even not quite negative 1. So this one doesn't look, this does not, can't be this one. So it has to be this one. And also, it does come up and touch right here at negative square root of 2 and turn around because of that even multiplicity, multiplicity 2. Here it's multiplicity 1 and it doesn't touch right here and turn around. It keeps going. And right here at positive square root of 2, it does come down and touch the x-axis at positive square root of 2, but then it does turn around, which it's supposed to. So, I mean, the same thing also happens here, but these are not the right values right here. So it's this one. And now we check. And there are those friendly green check marks, class. Okay, one more. 23. Same directions. This is a polynomial. The degree is 4. It's easy to start getting mixed up with degree and multiplicity. So degree, the highest exponent, 4. Which means when we find if we have any zeros, they have to have a total multiplicity value of 4 altogether. Okay. This is to the 4th power, even. So the end behavior has to be the same end behavior. Either they both go upward to infinity or they both go downward to negative infinity. How do we know which one? By looking at the leading coefficient. It's positive 2. And if it's positive 2, then we're supposed to remember. Or you can look it up in the book and write down the formula or the theorem if you want. I've been trying just to repeat it so that it kind of sticks in your mind. But you're always welcome to go to the section and write down a note if you like. So, okay. So when it's positive, both ends will have to go upward. And so both ends going up, well, all of these are both ends going up. So that didn't help us. So it has to have a maximum of 4 decreased by 1. Maximum of 4 minus 1 is 3. Maximum of 3 turning points. And I didn't mean to graph that one yet. I just clicked it by accident. So, well, we need to go to our paper and factor this. So here we are, number 23, 2x to the 4th plus 8x squared plus 6. So set it equal to 0 and try to factor this. Well, there's a times 2, there's a times 8, and there's a plus 6. We can factor out a multiply 2 if we like, which is a good idea because it makes the numbers on these smaller, which are easier to try to work with. There are 4 multiplied x's here in this term, 2 multiplied x's here, and no x's here. No multiplied x's at all. So we cannot factor any x's out of these 3 terms because there aren't any on this one. There has to be multiplied x's on all of them to be able to take any out. There aren't any here. So the only thing we can take out is a multiplied 2. So there's the multiplied 2. What's left in these 3 terms when we take out a multiplied 2, or we say a factor of 2? Well, 2 times x to the 4th gets back to 2x to the 4th. 2 times positive 4x squared gets back to 8x squared, positive 8x squared. And 2 times positive 3 is positive 6. So this is what's left. And we have this x to the 4th like we did in the last problem. It's down here, which we tried to factor, and we were able to factor this. Well, let's see what happens here. So, factor this. The 2 is still here in front, the multiplied 2, or the factor of 2 that we took out. So let's see. 2 terms here, 2 terms here. Let's see. I already worked it out so you could see it. So x squared times x squared is x to the 4th. So, so when you factor this, you have to say to yourself, what do I put here and what do I put here to get back to x to the 4th? Well, x squared times x squared does get us back to x to the 4th. So that's why we put that here and that here. How do we get a positive number right here? Well, it's either positive times positive, that's positive, or it's negative here times negative here. That would also give you a positive. How do you know which one? Do we write positive times positive or negative times negative? Well, it depends what's right here. So whatever is right here, you write it down. So positive times positive. How do you get 3? The only way you can get 3 is if you multiply 3 times 1. Unless you use some fractions or something. But 3 times 1 is 3. If we multiply this out, x squared times x squared is x to the 4th. X squared times 1 is 1x squared. If we multiply these out, sometimes I forget to multiply them out. And you kind of just do it in your head after a while. X squared times x squared is x to the 4th. X squared times positive 1 is plus x squared. Now I'll multiply 3 times these two. You get 3x squared. Positive 3 times positive 1 is the positive 3 we're talking about. And now this x to the fourth is that 1x squared and 3 more x squared adds up to 4x squared, which is this, and the plus 3. That means then when we factored it into these two factors, we did it correctly. So these are both quadratic factors because of the x squared. So they're not repeated. This is not the same factor. This is x squared plus 3, and this is x squared plus 1. So they're different. So no repeated factors here. If we now set each of these equal to 0, there's no x right here. So this doesn't count as any, this won't give us any x-intercepts because there's just a 2. There's just a number, not an x. 2 equal to 0 doesn't make any sense. So this does not give us any zeros or any x-intercepts. This will give us 2 of them, and this will give us 2 more. Total of 4, which is the 4. So we set x squared plus 3 equal to 0. We set x squared plus 1 equal to 0. And then we solve them. How do we move this plus, how do we get this addition of 3 out of there so that we can solve for x? What's the mathematical inverse operation of addition of 3? It's subtraction of 3. So subtract 3 on both sides, or you just move it over. 3 minus 3 is 0. 0 minus 3 is negative 3. So we get x squared equals negative 3. Move this one over and you get x squared equals negative 1. Now, we have these equations, but does this give us any real answers? If you take any number, multiply it twice, can it be negative? So for example, 3 times 3 is 3 times a positive times a positive is a positive. A negative times a negative is still a positive. So because this is x squared equals negative 3, there's no way you can take a number, multiply it twice, and get a negative answer. You cannot put the same number here and the same number here and have it equal to negative. Because whatever you pick, you say, I'm going to pick a negative number. Well, then you got to pick the same one here. Negative times negative would be positive. So there is no number you can put right here and the same number again right here and get negative 3. And in another section, we're going to talk about imaginary numbers and complex numbers. And that's what this one has. This equation does not have any real solutions, because whenever you have an x squared equal to a negative number, there's not going to be any real numbers that it will work. There is no number you can put right here that's a real number, square it, and get negative 3. And the same thing here. So there are no real solutions here, which means there are no x-intercepts. There are no zeros. There are no roots. No real ones, at least. There actually are 4 of them, but they're all complex numbers, which is not something that we can see. I know that's a little strange at the moment. But there are no real zeros. The maximum number of turning points, we already said that was 3. And now we go back to our WebAssign. Find all the real zeros of this polynomial function. If there are no solutions, put no solution. Well, there are no real ones. So we type no solution. The multiplicity, there's no real zeros, so there's no multiplicity of these real zeros, so no. turning points we said were a maximum of 3. Now the correct graph, well, we know that the tails have to both be going upward. We already talked about that because this is degree 4 and it's a positive number in front. All 4 of these had that. So that didn't help, we said. What does help is that this graph has no real zeros, has no real x-intercepts, which means the graph does not touch the x-axis at all. It doesn't touch it at all. Well, this touches it twice. This touches it once, twice, 3 times, 4 times. This touches it once, twice. These all cannot be correct, because this polynomial has no real zeros. So by default, it has to be this one right here. And now we check. Hopefully we are correct. And there are those nice green check marks, which means correct. So that's 23. We did 22. There's, I believe, 2 for you here. Oh, actually we did 3 of them. So I left you with this will factor very nicely. This will give you our repeated 0 when you factor it. This will factor down into 2 factors, or you can use the quadratic formula. This one, t squared equal to 0 will be t equals 0, but it's going to count twice, multiplicity 2. And this one's going to give us 2 more. And again, you can find those 2 by either factoring, parenthesis times parenthesis, and using your FOIL method to factor it down, or you can use the quadratic formula, your choice. And then you answer this as we did before. And this one is going to be fairly simple to factor. This one should be quick. And this one also is quick. X squared minus 4, you can factor this down, x minus 2 and x plus 2. And you already have your 2 factors. You can get your 2 zeros, and it should be fairly quick. All the rest we've already talked about, except for the very introductory questions, which I want to look at with you. So 1 through 6 are these introductory terms. So a factor x minus a, like an x minus 2 or something, to the kth power, which means like squared or cubed, or to the 4th power, yields, this gives us, remember, a repeated, because if this was like an x minus 2 cubed, it would be an x minus 2 times an x minus 2 times an x minus 2, and that's a repeated 0. Repeated. So repeated 0, the 0 would be x equals 0, x equals a, excuse me. It's the opposite of what's inside here, minus a, so positive a. And with multiplicity k. With multiplicity k. And that multiplicity can be odd or even. With a real 0, real 1, like the ones we can see, not like the last problem we just did, but all the other ones. With a real 0 of x equals a of a polynomial function, and if it has even multiplicity, if this 0 has even multiplicity, then what does that mean at the graph? When it's even multiplicity, does the graph cross and keep going through the x-axis? Or does it touch and turn around? When it's even, when the 0 has even multiplicity, it touches and turns around. It touches the x-axis at x equals a, and when it is odd multiplicity, it passes through. or you can say crosses. Crosses through, passes through. When x equals a is a zero of a polynomial function, the three statements below are true. X equals a comma 0 is called, that's the entire point, it's called the x-intercept point. Move this a over to the other side like we've been doing and you get minus a. X minus a is a factor. X minus a is a factor. And x equals a is a solution to this polynomial equation. When you set the equation equal to 0, then x equals a. If x equals a is a 0, then x. Then we also can say x equals a is a solution to this equation. And now let you all answer number 2 and 3. Number 1, the graph of a polynomial function I didn't mention this exact word, continuous, but I did mention to you that it cannot have any breaks or holes or gaps. Breaks or holes or graph. You can have smooth turning points, but no breaks or holes or graphs. And that's called continuous. Continuous. And then this should be pretty. I kept saying that term over and over. What helps us decide whether it's left-hand behavior or right-hand behavior is going up or down? Well, there's really two things. You have to know the degree, and then you have to use the leading coefficient test. So, leading coefficient. Well, now there's only one left for you. Okay. Okay, class, so I hope, well, we did a lot of them together, didn't we? Whoa, that's a lot. 1, 2, 3, 4, 5, of course those are short. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, I feel like I helped you too much. I'm going to take this back. No, there's still 12 left for you, but I do want to help you. That's what I'm trying to do for you. And you need to hear it. These are very not simple to learn all by yourself. That would not be a simple thing, unless you've already, unless you are willing, a person's willing to read the section, read all kinds of examples, and make connections. But I want to help you with that. So I feel that's my responsibility. So, okay, everyone. So again, I hope this will help you. I thank you for your patience. Stay tuned for the next one, which will be section 2.3. But until then, thank you again. I wish you all the best, and we'll see you next time. Okay.